Hello, everyone. Welcome to the SEAD webinars on cooling solutions. We had two parts for these webinars, and unfortunately, part one had a technical incident, so only the two last presentations were recorded, but please download the first one, which is available as a PDF on this website. Without further ado, I'll let you connect to the first part. Have a good session.
Wonderful. I think you should mute. Perfect. Okay, well, thank you very much, everyone. I am very happy to say something about the recent commentary that the IEA has published on cooling and affordability challenges in terms of cooling. So I guess I'm just going to dive right into it. Are we seeing the screen?
So you're just sharing your screen.
Are you?
I'm not sharing my screen.
Okay. Social action.
Yes. I thought we just taken the same.
Sorry.
Sorry about that. Very good. So just about 2 weeks ago, we published a new commentary that looks at trends in cooling and air conditioning, and it all really comes down to we are seeing a lot of increase in demand for cooling in the world. So what we see on this graph is that pretty much in every region over the last couple of years, the cooling degree days, or the measure for how much cooling is needed, has been increasing, in some regions more, in some regions less, but it generally has been the case. And now we're having relatively clear signs that this year will be a year with a relatively strong El Niño event, which means it's a surface water movement in the Pacific, which often brings along more extreme weather events across the world. So we can brace for more. So that comes in a context of, another crisis, which is the energy crisis and the constrained energy shipments from the Middle East, which has already led also many countries to implement emergency measures that also had to do with cooling due to a doubt about the availability of gas as a peak load, as for the plants that will cover the peak load, which are very important when they're cooling peaks during heat waves. Because actually, while cooling accounts for like 10% of electricity demand, it can go up to 30% of peak load in the moments when it's very hot. So that's a very significant amount of energy. So on the other side, air conditioners are being shipped, sold, and bought more and more across the world. We see in this left chart on the next page. We saw from 2020, when there were just over 150 million units shipped, and in 2024 was like the record where it hit about 200 million already, where in this year there was like a tremendous growth in India, the Middle East, the US and Europe of about 10%, and about 40% in Latin America and Africa. So a strong growth there. And then also, what does it mean in terms of households? How many people do have air conditioning? And we see already very high rates in the US and Japan of around 90%, and that has been relatively steady for a longer time. We saw a rapid growth in China of going from just over 50 to almost 80% over just 10 years. And also regions like India and Southeast Asia have been growing very much in terms of energy of air conditioner penetration. So that of course means the needs are there, and the growth is coming along with it, and that very much increases the energy demands. On the next page, we see it. So actually at the moment where we saw a growth, it's not on the slide, of about 50% from 2015 to 25. So that's quite a bit more, and it's now at around 2,900 terawatt hours, which is about the same amount as the entire electricity demand of the European Union, so that's quite significant. And it is bound to increase by another 1,600 with current policies over the next 10 years. And if we then see more heat waves, that's sensitivity case in our model, we can expect another boost of 50%. So cooling demand rise is very, very high, and it has to be managed right. So this is where we get to on the next slide. And very much as also Georgia in the first presentation has talked about, there are different ways of coming by this, and it is very much cooling. It's very much systemic actions. It's not only reducing or working on the air conditioners. So it starts of course on big like national plans, but then in practical measures on an urban level, the urban heat island effect is very real. It can mean that in urban centers can be up to 10 degrees centigrade higher than the rural areas. So that's very much. And mitigation actions include green spaces, bodies of water, greening of the streets, and unsealing of pavement to have evaporation in the street. And each of these can be reduced by up to 5 degrees the temperature again. Buildings can be the orientation of the building can be adjusted, the shape can be adjusted, insulation. So there's many things in buildings that can be done to just decrease the heat gain, and passive measures like shading and ventilation are playing, of course, an important role to just bring down the need for active cooling as far as possible. And also individually, it can be combined with fans to just bring down that demand. Still, though, there will be air conditioning, and that has to be as efficient as possible. And as we see here on the right side, the cost of a 25% more efficient unit in upfront cost and energy cost is generally lower in most regions than in other regions, than the baseline most sold model at the moment, which can just like decrease all of these grid pressures. And on the next page, we have run analysis here at the IEA, where we had people in 3 regions in Southeast Asia, in Latin America, and Sub-Saharan Africa that basically went into shops and looked at what energy efficiency do the devices that are being sold there have, and what were the prices of these. And what we found is that in all of these regions, you can find a much more efficient model for roughly the same price as the more efficient, as the less efficient model. So it's really down to choice. So how do these two things go together? On average, the more efficient model does cost a little bit more, but you can find the more efficient model also for a more efficient model also for the same price as the less efficient one. So how do these two go together? And our colleagues from 4E have done a very good analysis on this. So I'm handing over to Kevin Lane for that. Thanks very much.
Thank you, Fabian. You want to mute? Right, so the question
you've just seen, which Fabian has posed, is just this issue that always comes up: just do more efficient equipment costs more? And this is one that we'll come to as well. So what we're doing here is also looking at different ways we can get this data as well. So Fabian showed a very nice way that you can get these crowdsourcing ways of getting information on the products that are being sold. What I'm showing you here is a slightly different one. Here's something where we looked at web scraping. So you go online and trying to get the information of products that are being sold. So it may not be representative of all sales in India, but increasingly online sales are a good surrogate for the price and what's actually on the market. So this was a web scrape that we did a test in April 26, so earlier this year, just to see what the products on the market were looking like. And if you look at the bottom right, that is the efficiency across the bottom and the price up on the left-hand axis. So there's probably just a little bit of a correlation that the more efficient ones do cost a little bit more, but you can get an efficient one that doesn't actually cost that much more. And because we've scraped a very good data set, what you can do is run an ordinary linear regression using dummy variables for the brands, and you can then get something comes out and says what's really explaining the price is that actually larger equipment are the ones that cost more, which is what you'd expect. But also brand can be a major factor as well. So in India, it was General is a very high quality brand, and that costs you an extra 26,000 if you want to purchase that. So that was the bigger one. And there was a much smaller efficiency effect as well, so that more efficient ones were a little bit more costly to do. But that could also be that there was new regulations that came out on labeling that came into effect this year. And you can see that on the top that the 5-star ones are now at 5.6, and all the categories the manufacturers or suppliers are just getting them to just go over the thresholds of those. So we'll develop this a little bit further, this type of analysis, and we'll do it for more countries and see what that looks like. But it's an interesting approach and some nice findings.
All right. Thank you very much. So we're running late, so I think I will now give the floor to Patrick Blake directly. Patrick, over to you.
Great. Thank you, Sophie. And I'll share my screen from this side.
We can't hear you. You're muted.
Hello? Can you hear me?
No.
Can other speakers hear me?
No. Was working earlier.
I can hear you, Patrick. Sorry, Georgia here.
Hi, Georgia. Thanks. Yeah.
No, still not.
But it's us.
What?
Yeah, I
It's
think
us. It's not the.
perhaps in the interest of time, I'll continue.
Okay.
Okay. Wouldn't be a webinar without technical difficulties. So I'll share my screen from this side. And full screen. I hope you're able to see my presentation. Apologies. Sophie, could you just confirm if you see my presentation?
We don't.
Try that again. Do you see now?
Yes.
Okay, great. Thanks. Okay, yeah, thanks so much to the IEA SEAD colleagues. It's been a pleasure to participate today, hear all the other updates. I'll be brief because I know we're ahead on time. So again, I'm from UNEP's United for Efficiency, and I'll give a presentation on our country savings assessments. These go hand in hand with another tool that we have, the model regulations, and were referenced by a few others already today, and we had a separate webinar with SEAD on that. So today I'm focusing on the country savings assessments. But that's really a tool. The model regulations is really a tool for setting MEPs on the cooling products and other products as well. On the country saving assessments, so this is a tool that we've developed over 10 years ago and shows the savings potential for energy efficient products. So lighting products, electric motors, but today I'll focus mainly on the cooling products, air conditioners, residential refrigerators, and commercial refrigeration. It's a assessment that's available for all developing emerging economies, and it shows the savings across electricity, greenhouse gas mitigation potential for both direct and indirect. So if from electricity and also from the refrigerants as well. And on electricity bill savings, affordability has been mentioned a few times, so it also shows that savings and puts it in other equivalencies, so putting it in power plant saved as well. It's available on the link there, and I'll show you more details on it. Just to give you a sense of what it looks like in terms of the savings, this is it's not global, it's all developing emerging economies, and it shows the savings across the products that we work on, so that I referenced earlier. Over 1,200 terawatt hour savings, significant greenhouse gas savings, but as mentioned earlier, also significant electricity bill savings. So on the cooling products and the other ones referenced through efficiency measures, through more efficient products, would be able to save $110 billion per year in annual savings for consumers or businesses. That as well is related to equivalent to 550 power plants. So given the energy crisis, certainly beneficial there as well. And on the graphs there really show you, I think other presentations really showed the growth of consumption on cooling products. This goes out to 2050. On the right-hand side, you really see the opportunity for cooling. The gray area is room air conditioners, so by far the largest opportunity across countries, but there can be differences for cooler versus warmer climates. But still significant savings for residential refrigerators and commercial refrigeration as well. Then in terms of what the country saving assessments look like, and I'll show you on our website, the interactive part, but we have a individual assessment for the 150 countries incorporated in this assessment, and you can see it here. So it has multiple tables and graphs really demonstrating the savings in terms of electricity, greenhouse gas savings, and breaking that down in years and also by product categories. So allows users to really go into that. We also have regional savings as well. So groups of regions that we work closely with, like in Southeast Asia and Southern Africa, where they're working together at the regional level in terms of harmonization. And there it is available on our website, and I'll briefly show you that in terms of the websites. On our website, I hope you can see my screen. Just to briefly show you how to interact with that. So on the country savings assessment page, you can select the country. Here I've selected Thailand. You also can change the year when you want the results, and also the comparison year. It gives you a heat map showing this is based on consumption. So across the different product categories, allows you to see where the consumption savings will be in different scenarios. You're able to as well focus on different product categories. So could focus on air conditioning if that's my interest, and look at the savings across that. Just to really show a few further points on this, as I mentioned earlier, there's different scenarios. Those scenarios are linked to our U4E model regulations. So the business as usual is assuming no policy development. The minimum ambition scenario is the entry level level of efficiency in our model regulations, and then the higher ambition one is a higher level within that. So allows government officials or others to really see opportunities to increase their maps more ambitiously. Further down, you can see it for the individual country, the total energy consumption and the savings that they could have across those different scenarios. As well, here you see it broken down by the different product categories. So this could help a government official prioritize what areas they should focus on, because it allows them to see across those different product categories the savings opportunity as well. Then just to point out a few other quick things. There's a lot here, so I won't go through it all. But in addition, above, we saw the savings from electricity consumption. For the cooling products, we also have the savings potential for direct savings from the refrigerants as well. So that's something available there as well. Then finally, you can generate a report which creates a individual PDF for the country, and then that's available for download and printing as well. You can focus it on different product categories, so it allows you to focus on lighting or cooling or equipment. Then last point from my side as well is, as I mentioned earlier, there's regional assessments available, and that allows you to, again, look at particular regions and the savings opportunity there.
Hello, everyone. Thank you for joining us and welcome to today's SEAD webinar on cooling solutions, where we're looking at global insights for policy and practice. During the first part of this series, we recognise that cooling is a very complex topic, and there are many measures that need to be taken to cool our buildings efficiently. But because we have an immediate problem with heat around the world, we're concentrating just at the moment on air conditioning. Last session, we talked about the building blocks of appliance policy, the testing, the performance levels, comparing those performance levels around the world, and highlighting the fact that more efficient air conditioners don't have to cost more, and they're less costly to run over their lifetime, but they don't have to cost more to buy. Just a quick word about SEAD, if I may, on the next slide, just to say that SEAD is a collaboration, a voluntary collaboration between 23 governments, and it is homed by both the Clean Energy Ministerial and the Energy Efficiency Hub. And the idea is to promote energy efficient appliances and lighting and equipment worldwide. It's a place to share information on a voluntary basis and help us work out how to make more happen faster in terms of energy efficiency. So for today's session, this is our agenda, if we could have, thank you. So we want to talk today, we talked about the kind of nuts and bolts, like I said, the first time round. This time we're going to go through a series of case studies to illustrate what's being done around the world. So we're going to talk about fans. This is something that people don't talk about very often, but they're an undervalued asset for cooling, and they deserve dedicated policies for them to be more efficient and more widely understood, the utility to be more widely understood. We will talk a bit more about regulation, and this is in the context of how this is done in the European Union. We're going to talk about some technology options, and this is going to come for, we want to talk about how we could double the efficiency of room air conditioners, and we're going to hear from CLASP on that. And then we're going to have an example of accelerating India's cooling transition from sustainable energy for all. And then we're going to wrap up with a very important presentation from a utility. So Jiangsu State Grid Company in China, where we are looking at the utility we get from using demand response with air conditioners. So hopefully everybody will find this a really useful set of examples for how we can improve cooling. And I'm going to hand back to Sophie to kick us off.
Yes, thank you, Mel, and good morning or good afternoon, everybody. Before we start, we just wanted to highlight 3 key facts about air conditioning. So in the next slide, the first one is that to remind, especially in times of energy crisis, that simple action can really make a difference. This slide shows that if you choose efficient appliances, so efficient ACs, and if their temperatures are set at a reasonable set point, and even if you add the consumption for a fan, this is the little bar at the top, you can half the consumption or more than half the consumption for air conditioners if you find a good appliance and you set the temperature at 26 degrees instead of 22 degrees. So there are more behavioral in the choice of appliances and in their use that can aspects that can really make a difference. The second aspect is that energy efficient appliances and air conditioners in particular are very beneficial, very profiting to consumers. If you look at the overall cost over the lifetime and you separate the upfront cost when you buy it, this is the bottom of the bars, and the cost in electricity over their lifetime, the efficient appliances on the right is more profitable. It costs less to consumers. And actually, if you even look at the upfront cost, it's not that different between a low efficiency model and a high efficiency model. And we saw last week that in our research at the IEA from market data, we see very clearly that with the same amount of money, it is possible to buy an efficient model or an inefficient model on the market. And lastly, we also know that peak loads are highly impacted by air conditioners. So this graph shows that for 1 additional degree in the temperature in India, you have a huge difference in the peak load that is requested to have all these ACs working. But you also see that thanks to energy efficient air conditioners, you could avoid several gigawatts of peak loads. And this is really critical also for energy security so that the grids are stable. So with this in mind, let's go directly in the topic, and I will hand over the floor to Jerry George. Hello.
Thank you, Sophie. I'll just share my screen. My screen is visible, right?
Yes, absolutely.
So hello, everyone. And first of all, thank you to the IEA and the SEAD initiative for inviting NRDC India for this webinar. I'll start with a brief context. India sells about 60 million ceiling fans every year, and the total, one second. Yeah, India sells about 60 million ceiling fans every year, and the total number of fans in use is expected to grow around 450 million today to nearly 950 million in the coming years. So we are about to double one of the largest electricity loads in Indian homes. Yet, this remains an overlooked part of our energy system. The opportunity here is huge and very straightforward. Super efficient ceiling fans using BLDC and improved induction motors can deliver the same comfort while using much less electricity. The technology already exists. The challenge is, how do we scale it? How do we make efficient fans the default choice? It should be affordable, reliable, and made in India. To answer that question, Natural Resources Defense Council, together with our partner Greentree and with support from the Department of Science and Technology, Government of India, developed this blueprint. It is a national roadmap to make super efficient ceiling fans the standard by 2030. The roadmap is built around 3 priorities: higher efficiency, better affordability, and stronger domestic manufacturing. It also recommends 4 key actions: better design and materials, stronger testing and quality standards, creating demand through incentives, procurement, and awareness, and building the ecosystem through research and development, testing, and manufacturing support. All this is about changing the whole market. So if we get this right, we can reduce electricity demand at scale, lower electricity bills for households, and strengthen India's manufacturing base. And most importantly, this blueprint is based on extensive consultation with the industry, government, academia, and other stakeholders. So it reflects what is practical and achievable. So let me briefly talk about where the technology stands today. There are 2 motor technologies in the market. The first is induction motor, which is reliable and low cost but less efficient. The second is BLDC motor, which is much more efficient but still represents a very small share of the market currently because of its higher cost and some durability concerns. Today, induction fan typically reaches a service value of about 6, while BLDC fans can reach around a service value of 7.5. And basically, service value is the measure of how much air a fan delivers for every watt of electricity it uses. The Bureau of Energy Efficiency in India baselines around 210 cmm of air delivery. So that's the reference that we are using across this analysis. The important point is that the technology has much greater potential. Improved induction motors can reach around 8.4 service value, while optimized BLDC motors can reach about 10.5 service value. That's roughly 40 to 75% improvement over where most of the market is today, which is around 4 to 5 service value. So what is the whole vision behind CF30 or 2030 vision for ceiling fans, what we are calling? So by 2030, we want a 5-star ceiling fan to become the new normal. That means a fan that uses 24 watts or less, delivers 210 cubic meters or more air deliver, and the cost is around rupees 800 INR or around $18 per se, which is close to the price of today's 3-star fans in India. And it is at least 80% locally manufactured. Today, most of the 5 stars are BLDC models costing around rupees to 2200 to 2500. Our goal is to bring that performance down in cost while making it affordable at scale. One of the things that people often ask whether we can replicate the LED program in India for ceiling fans. I would say the opportunity is certainly huge, but the challenge is more complex because fans require change across the entire value chain. In terms of affordability, most consumers still buy fans based on the upfront price, so financing or incentive programs may be needed. Secondly, we need a stronger domestic manufacturing base, importantly because for BLDC ceiling fans, the components such as magnets and electronics are still largely imported. Thirdly, we need to improve the reliability, testing, and servicing ecosystem. Consumers expect fans to last for many years, so better controllers, stronger quality standards, and trained service technicians are essential. Finally, the greater consumer awareness will also be very important in terms of people buying fans based on airflow, comfort, durability, and trust, not just electricity savings. So how do we get there? First, better design and materials can improve efficiency to 10 to 20%. The technology already exists, but wider adoption is needed, especially among small-scale manufacturers. Secondly, we need stronger collaboration between industry and academia so that research is translated into practical products. This blueprint also recommends approaches like Innovation Challenge and Center of Excellence to encourage joint problem solving and product development. Thirdly, improving controller reliability and updating testing standards are critical for building consumer confidence. On the demand side, we need greater consumer awareness, better labeling, public procurement, and utility-led programs can help accelerate the adoption of efficient fan. Finally, we need to strengthen the broader ecosystem through more testing facilities, R&D infrastructure, and greater domestic manufacturing of key components, especially the magnets and electronics. Together, these interventions provide a practical pathway to making efficient, affordable, and locally manufactured ceiling fans the new standard in India. I'll stop there. Thank you again. And the report is available online for you to read more in detail. Over to you, Sophie.
Thank you very much. That's very interesting. I hope the Indian government follows the whole plan that you have prepared. I really like fans. So I have written in the chat, if you have questions, please write them in the Q&A box and we will try to answer in writing because we don't have much time. Maybe at the end we will have 5 minutes left for questions. So we now go to Europe and Philippe Rivière will present us the new expected regulation for ACs. Philippe, over to you.
Thank you, Sophie. Yeah, so good morning. My name is Philippe Rivière. I'm working in the European Commission, Direction of Energy, in the unit in charge of buildings and products policies. So it's now about 50 years that Europe has been regulating or trying to regulate the energy efficiency of products through energy labeling and minimum performance requirements. We have more than 30 products covered, a large share of the EU consumption, and we are trying to maintain and improve this regulation over time. And today I will focus on the regulations for air conditioners and their revisions. Next slide, please. So these two regulations are the eco-design, which is most commonly known as MEPS in the world. So minimum energy performance standards that remove the worst performing product from the market. So this was adopted in 2012 for the first time. And in 2011, we revised the energy label together with these MEPS. Beforehand, we already had a label since 2002. So this serves as a pooling mechanism to increase the efficiency of the products. So these two regulations were adopted in these years. The scope covered is up to 12 kilowatts. In Europe, we have mainly the development was done on split system. That's the most common system. But the requirements also cover other type of air conditioner like window air conditioner portable. And we have specific requirements for portable air conditioners that are quite common in Europe, in particular single ducts and double ducts. At the time, we included comfort fans, but we had limited data, and so we just set information requirements to be able to legislate afterwards. And in this regulation, there is also close control air conditioner as part of the scope, but in practice, there is no metrics, no requirements. And most likely it will be developed further in the coming years with large air conditioner policies. Next slide, please. So in 2012, for the first time in Europe, for the most common type of air conditioner, the split type, were introduced seasonal performance metrics, so including the part load of appliances, with relatively ambitious minimum performance requirement, both in cooling terms, so in terms of seasonal energy efficiency ratio, and in heating metrics, so seasonal coefficient of performance. There are separate requirements for portable air conditioners, so single duct and double duct, that are still on nominal basis. Additional characteristic of this regulation is that we have also introduced in Europe a maximum sound power level to protect consumers. So the product information on the comfort fans I was mentioning before, and also we have specific requirement for off-mode and standby power inside this regulation for the portable air conditioners and the comfort fans. For the split air conditioners, the impact of these modes is integrated in the seasonal performance metrics. And another innovation was the introduction of a refrigerant link. So to help with the development of alternative refrigerants, there is a possibility to have lower efficiency for low GWP refrigerants. Next slide, please. So together with these MEPS were an energy labeling regulation, which is still in force. So specific scales were tailored for the different metrics. So seasonal on one side and nominal on the other side. And so you can see that there are 5 slides for heating, 5 scales, sorry, for heating and cooling. And so on the specific design on the label, Of course, we advertise the kilowatt, which is needed to design the appliances, the efficiency, but also the noise and the indication of performance for different zones for seasonal metrics because of the large variations. Next slide, please. So we started the evaluation of these policies a few years ago already. So the first thing is to evaluate how far they were effective and efficient. And so in terms of effectiveness, they behaved as expected with relatively important savings given this still small end use in Europe. And this is only, so the measure were taken with main effect in 2013 and 14. And so it's only half time of the product lifetime. So these gains are still increasing significantly. But in the evaluation, we see that there is potential for improvements, and we plan to update this regulation and make them more stringent, and also update them with the technological progress. Sorry. So in particular, we see that there is a significant difference between real life behavior and what is evaluated in the matrix. So first, for the portable air conditioner, the single duct, the infiltration effect is not accounted for. And this, in particular, when it's very hot outside, has a large effect on the ability of the product to cool the house. And it also is detrimental. It's also because single duct and double duct are not treated the same way. It also modifies the market deeply. So we need to correct this and integrate the infiltration, probably by adapting seasonal metrics also for portable. And for split air conditioners, we see that there is, even if we are already at seasonal, there are problems with the metrics because of the way the tests are done. And so there is also a potential here to improve. And we also see that some of the products increase their efficiency with having high airflow, which are not realistic for end user in the end. And so also here, a potential gap between real life performance and standard performance that can be corrected. Beyond that, the evaluation has shown that there is a large potential to increase the efficiency at lower life cycle costs for the end user, as was shown previously by Sophie. And we also see that what was planned for comfort fans didn't work. We don't have more data today than before, so we need to change how we do that. And also we can see that the label need to be updated because they are no longer not ambitious enough in cooling mode for splits and not working at all for single duct. These products are still very close to the minimum performance requirement. Next slide, please. So based on these observations, we have been discussing possible revision projects with the member states and with the stakeholders. So you can see here the proposal to adapt the minimum performance requirement. So for split air conditioners, we found that it would be possible to go up to a seasonal performance value in cooling mode of 6 and heating mode of 4. And if you look already now at the market data on the product registry of European product April, you can see that manufacturers already anticipated these thresholds. So this is already the minimum efficiency is already at this level. And then we have also planned more ambitious requirements in terms of seasonal performance for portable, and we would like to introduce a new category for fixed double duct, which is still small but has specific technical characteristics and could develop in the electrification for apartments. There are additional proposals. So first, we see today we offer the possibility to label a heating function for portable. We think that it's not a good idea, or at least it should be referred with high seasonal performance requirements, including infiltration. As indicated before, we will need to limit the airflow to avoid increasing the gap between real-life performance and what the end user really can expect. And there is a specific topic which is still being debated, which is the link with the refrigerant, because The F-gas regulation that is changing banning progressively the high GWP refrigerant has strong impact. And most of the products that are today on the market will not be on the market tomorrow. They will have to move progressively to R290, the propane, or to other natural refrigerants. And for some of the product segments, so for multi-split and large splits, there is not yet product on the market, which makes it more difficult to plan for this future requirements. So we are still debating on these points. Next slide, please. On the energy label, we have also increased the ambition. So we see today that we have various scales for cooling and heating products, not only for air conditioners, but also for other local space heater using gas, oil, or solid fuel. And end user, when they see the different scales with the same letters, they think that the performance are comparable in average. Huh? And so it means that we should try to make these scales comparable. So we are trying to introduce a merge label with only one scale for all the kind of products to steer the consumer to the most efficient one. In this particular case would be heat pumps, so air to air, for all the room heating appliances. And we have then tried to adopt the same policy for cooling, putting on the same scale split air conditioner and portable so that people can see the difference in efficiency between the two categories and not only amongst one single category. So this is the main change we are planning for the label. And again, it's still being debated. So you can see here some specific scales which were proposed in 23 for discussion. Next slide, please. And finally, the last change is that we think we need to adopt also performance requirements for fans, both minimum performance requirements and an energy label. So this is now the plan, and you can see the class, an outline of the classes that were discussed in 23, and the minimum performance requirement for the various type of fans. For ceiling fans that are much more efficient, different requirements, and then for all type except tower, so you can see different lines there. Yeah, so this is only a proposal being discussed, but not yet the final values, of course. Next slide, please. So for the revision process, we started already in 2019, even before for the revision, but we are still working on that, so it takes a long time. The next step is to have the impact assessment submitted to our internal scrutiny boards of the Commission and accepted, and then we could have the regulation published in 28 and enter into application in 2030. So that's the plan at least. Next slide. So the question will be either, I understand, but if you want more information on energy efficiency policies on products, you can find here the link. You can also find a link where you can find all the documents being discussed with stakeholders and member states regarding the revisions, specifically for air conditioners on CRKBC, and the link with, to the database of products with an EU energy label. Thank you very much for your attention.
Thank you, Philippe, for this very interesting and very complete presentation. I have just one question because it will relate to our last presentation. Does Europe plan to have a specific item on the label to signal smart appliances?
Yes, so we have already agreed to do that for space heating and water heating, and it will be probably the case also for air conditioners. There will be an icon on the energy label to show interoperable appliances able to do demand response.
Thank you very much. So now we're expecting this new regulation and expecting more efficient appliances to come on the market. And I will hand the floor over to Haijin Tian from CLASP China to tell us how do we get to have very efficient appliances on the market. The floor is yours, Haijin.
Thank you, Sophie, and hello everyone. I'm Haizhen Tian from CLASP. In CLASP, we take the mission to improve the energy and environmental performance for the appliances and equipment we use every day. So today it's a real pleasure for me to be here to talk about one of the most important energy challenges we are facing today, keeping people cool in an efficient way. So what I want to share is a simple but powerful message to doubling the energy efficiency of room air conditioner is not a distant hope. It is technical feasible today. With technology, we already understand. So let me walk you through how to do so. To see where the opportunity is, we first have to know where the energy actually goes. In a room air conditioner, it is essentially a loop. It has a handful of core parts you can see from this finger, and compressor, condenser, evaporator, fans, and also the control parts such as a valve. And all of this working together, they circulate a refrigerant to cool our room. Now, if you take just one thing from the slide, let it be like this: the compressor, which is the heart of the machine. It pressurizes the refrigerant and keeps the whole cycle moving. And also, it is by far the biggest energy user in the machine. At the chart on the right shows the compressor typically accounts for around 80% of an air conditioner of electricity use during a rated operation. So in traditional air conditioner manufacturing, the goal was fairly simple: achieving energy saving meant to keep the compressor in its optimal operating condition. But as technology has advanced, our range of options has grown well beyond that one component. So let me turn to next slide to discuss how technology is driving efficiency improvement across the whole system. Here, how do we actually make an air conditioner more efficient? Broadly, there are two main technology pathways, and you can see both on this slide. The first is component upgrade, improving the individual parts. That means advanced compressors and inverters can run smoothly even at a low speed. Second is larger, better designed heat exchangers using superior materials and refined tube designs. The third aspect comes from high-performance DC motors paired with efficient fans that can streamline airflow and cut turbulence. In addition, also mentioned by Sophie, smart sensors together with possible expansion valves can fine-tune refrigerant flow as cooling demand changes. But there's an important shift in the recent years. The focus has moved from optimizing one component at a time towards another pathway, system-level optimization. This is where the real game now comes from. Instead of just fitting a better compressor, we matched in this pathway, we match and tune all the high efficient components to work together. And also, we add the smart controls and AI algorithm that predict cooling demand and optimize the machine's operation in real time, even make a responding to signals from the power grid and ambient temperature or climate focused. Personally, I believe that as we push our AC efficiency higher, the system level thinking will only become more important. It's no longer about one better part. It's about the whole system working intelligently as a one unit. So as taken together, these advances are exactly what make our goal, doubling the energy efficiency and meeting a more ambitious standard. Not just necessary, not only necessary, but also it is a technical feasible. Here, what are these mentioned specific technology options? This table lists some key technologies, what our research found. One important note here I want to mention, these figures in the column are based on China's current RAC market, the products and also the technologies commercially available today. So they reflect a real-world option, not from laboratory scenario. Before we read the table, let me quickly explain the metric. It is APF, means annual performance factor. It is a metric deployed in China, RAC maps. It reflects annual energy efficiency. A higher APF means more cooling and heating per unit of the electricity contribute to. Here, for each technology option, we estimated two things: how much it improves efficiency and how much it adds to the manufacturing cost. For example, the inverter optimization and fan system improvement each add roughly 5 to 10% efficiency at a low cost. And the high efficiency compressors add to 3 to 8% efficiency with an acceptable cost. All this technology keep improving year after year. Others deliver big jump at a moderate cost, such as the microchannel heat exchanger can add 10 to 20%. The intelligent coordinate control is 8 to 15%. And also for cold climate, request heating, space heating, the vapor injection cycle can raise heating efficiency by 15 to 25%. At the same time, we should know that no single technology doubles efficiency on its own, but should be combined and matched to the market. And more importantly, efficiency and cost raised together, and past upon returns will be diminished. So the aim is a balanced pathway that avoid a high efficiency, high cost traps. The same concept has been mentioned by our NDRC colleague, affordability. Here in our research, the team used a case study that ties everything together towards an ultra-high efficiency RAC. We took China's best performing RAC on the market today as our starting point and modeled the full package of technology needed to push them further, combine this the component and system upgraded we just discussed. The result is reaching an APF from 5.2 to 6.25, which approximately equivalent to a CSPF of 9.15. Here we can see it is a 20 to 30% efficiency gain is achievable with technology that already exists today. And the target is to get there within about 10 years, while holding roughly 10% of the cost increase. The table here lists the specific measures in that package we have discussed. So doubling the energy efficiency of RAC is really ambitious, but technically sound. The technology is ready. What we need now is a policy support, such as standard incentives and market signals, to bring all these ultra high efficiency products to be scaled. If you want to explore the full technical analysis, our report is linked at the bottom of this slide. This is I want to share today, and thank you.
Thank you very much. Super interesting. I really love to hear that everything is already on the market and nothing new, nothing, no research needed, no time to be lost. So we hope that indeed the policies will follow up and will be ambitious to support these appliances. Thank you again. And that's a good transition to our next speaker, Ashish Jindal from Sustainable Energy for All, because he will speak about a program exactly on the super efficient models and how we can replace the old ones in the homes in India. Ashish, the floor is yours. We can't, you're muted. We can't really hear you. It's from very far away, the sound. Say something more. Not really.
Is it better now?
Yes. Yes.
Okay, great. So thank you, Sophie. And if you could pull up the slides. Yeah, so hi everyone, thanks for joining. Today, I would like to make the case for why India's air conditioner stock is one of the key climate and energy opportunities we have, and what an AC replacement program could look like to capture it. Let's move straight into the global picture. Next. There are over 2 billion air conditioning units installed worldwide today. As per IEA, by 2050, the number will hit around 5.6 billion. To put that in perspective, about 10 new AC units being sold every single second for the next 30 years. This isn't a niche appliance category. It is one of the fastest growing electricity loads on the planet, and it is highly concentrated. China, India, and Indonesia together will account for half of all AC units on Earth by 2050. China alone already sells around 53 million units a year, more than the next several markets combined. Next. So what does that stock mean in energy terms? Space cooling already consumes about 2100 terawatt hours a year. That's more than 2.5 times the entire electricity use of continent of Africa. That's roughly 20% of all building electricity demand worldwide and about 10% of total global energy consumption. It's also responsible for 1.7 billion tons of CO2 equivalent emission a year, which is 3.2% of global emission once you count refrigerant also. And here's the part we should really get your attention. Only about 15% of 3.5 billion people living in hot climate today even own an AC unit. So this curve is going to accelerate in coming time. Next. Here's the opportunity hiding in plain sight. The IEA finds that the average AC bought today is only half as efficient as what already sitting on the shelf in the same market. No new invention is required. This is just a purchasing decision problem, not a technology problem. And the payoff is immediate. Replacing a 10 to 15-year-old unit with a modern high-efficiency model could cuts cooling cost by 30 to 40%. Next.
We lost the sound. Ashish, we lost the sound. Ashish, can you hear me? Can you hear me, Ashish? Can you? Ashish, we lost the sound. Say something.
Hello.
Yes. Now it works. Thank you.
Sorry. So yeah. So basically, and the So this $2.9 in avoided investment, fuel, and operating costs, that is 2x improvement in average global AC efficiency, achievable just through maps and labeling. Next. Today, the AC stock sits mostly in China and US, but the next wave looks like completely different. Southeast Asia stock is set to grow ninefold between 2020 and 2040 under current policy settings. Over 80% of new electricity demand through 2050 will come from emerging and developing economies. That's where the work we set matters most. Next. It's not about total energy alone. As we get into energy get used, New York evening electricity peak jumped 90% above its off-season average during last year heat waves, when the AC ownership is high. Similarly, at France, we have seen, although there is a lower AC ownership, but there's a 25% jump in the peak demand. In India specifically, peak electricity demand rises by 7 gigawatt for every 1 degree Celsius of warming. And if every new AC sold through 2030 were high efficiency, we could cut peak load growth by 20%. So replacement is not only the bill saving story, it's a grid resilience story. Next. SEforAll already works in. We are supporting National Cooling Action Plan in various countries. We are supporting on Global Cooling Pledge. We are running cooling efficiency marketplace workshops in Ghana, Kenya, and Nigeria, and developing heat action plans for 8 Kenyan county governments. Already, we have mobilized more than $300 million in cooling investment, and that brings track record to India. Next. Now, specifically to India, space cooling already makes up close to 10% of India's electricity demand. And by 2050, the IEA projects this could rise to 28% of total consumption and 44% of total peak load. And this is really just the beginning. Only 13% of Indian households own a room AC today, compared to 90% in Japan and 60% in China. India sold 14 million room AC last year and are heading towards a billion unit in operation by 2050. On this chart, you can see building/cooling emissions are already about 12% of India's GHG footprint. Next. India owns cooling action plan. Break down this clearly. Space cooling is 57% of total cooling energy demand, ahead of transport AC and refrigeration combined. Sectoral cooling demand roughly triples across category between 2017 and 2028. And if you look specifically at space cooling electricity use, about 135 terawatt hours a year today, room AC alone account for 42% of that, which is the single biggest lever we have today. Next. This is just the analysis. It's already a policy direction. Last year, we had worked on National Conference on Sustainable Cooling, where we identified 2 clear priorities. One is to undertake a replacement program, and second is to develop innovative financing model to drive market transformation. Next. So here is the opportunity. Out of about 18 million AC installed, 60% of them could be 10-year-old, which could be inefficient, and those could be replaced with 5-star and more. And also the refrigerant could be replaced, and that could give 48 gigawatts and $6 billion of savings through this. Next. Here's the concrete place to start. We are already in conversation with PSU townships across more than 370 public sector undertaking and about around 800,000 plus residential units. There is about 1 million old rooms ACs in operation. Swapping them over 5-star rated unit would save significantly in million units in electricity cost and payback along with the refrigerant. Next. So it brings us together that the technology already exist. The savings are proven. The policy direction is set. What we needed now is finance replacement program to start with PSUs, townships, and to scale national-wide and globally. I'll pause here and hand over to Sophie back, and you can reach me to my email ID. Thank you so much.
Thank you very much, Ashish, for this presentation. It's very impressive numbers, a bit scary, I must say, but that's the way it is. So this replacement program, if it is implemented, will really have impressive results. So that was a very full, a lot of information in a very short time. Thank you very much. For interest of time, I think we have to close for today. I thank again all the presenters and hope to welcome you and the participants for new editions of SEAD webinars very soon. Thank you.